Oh, yes, exactly. State estimation. And what is state estimation? It's about knowing in which location the robot is. So one raw way of getting the state estimation of a robot is, for example, by using odometry. But the problem of that is that odometry gets an error that is increasing over time, and it's usually not small. So for that, we can use Kalman filters in order to mix the odometry signal with the signals of other sensors that provide a better odometry, like IMUs, for example. So that is the subject of the talk now. So it is my honor to introduce you to our speaker, who is Thisas Ranhiru. He is an electrical engineering student, and today Thisas will be talking about state estimation with Kalman filters in ROS2. Please join me in welcoming Thisas to the stage. Hello, Thisas.
Hello, Ricardo. Thank you for the introduction.
Oh, my pleasure. How you doing? Are you
Ah,
ready?
could you hear me?
Yes, we can.
Ah, thank you for the introduction, Ricardo.
Yes.
As he said, we'll be doing an introduction into robot pose estimation using the robot localization package with the BotBox system. So in this case, we'll be answering the question, where am I? So before I talk about the system itself, let's talk about who I am. So who is this guy telling me stuff about this pose estimation, right? So hello, my name is Thisas. I am, as Ricardo said, electrical engineering major from the Rochester Institute of Technology. Uh, I also happen to be an intern at the Construct. You may have heard my name if you have been attending the open classes. I'm responsible for some of the newer uh, notebooks in the ROS checks. So you can check out some of the work in learning robotics. Uh, for me, uh, in terms of robotics, a lot of my experience comes in working in the AI and robotics club here at our university, which means I get to play with a lot of cool and interesting robots. And given this experience in playing with these robots, uh, there are some challenges that come with robotics that are common to a lot of different types of robots. And one of those challenges is localization and in turn pose estimation. So let's talk about what pose estimation is, right? What is this robot pose estimation? What is a pose? So a robot pose is pretty simple. Think of it like a position in a chessboard. Or if you ever played Battleship, the position of your opponent's battleship, right? You give a simple coordinate, in a sense, like A12, and then the opponent knows exactly where you are. Similarly, it's a way of telling the system where your robot is in 3D space. So we have an X, Y, Z, and we have an orientation. If you, the moment you heard X, Y, Z and orientation, you might be thinking, oh, I know what this is. This is odometry, right? This is the odometry message. Um, and you're not wrong in the sense that the odometry message does have a lot of these, but odometry itself is not the only thing that's used in pose estimation. In fact, using the robot localization package, we can combine multiple different types of sensors together to form one cohesive pose estimation. And there are several reasons why we would want to do this, and we'll be going through the advantages of why we would set up such a system by seeing the disadvantages of just relying on odometry. One of my favorite implementations of these types of full systems, you can see it's almost very close to the example image, is these food delivery robots. In practice, the goal is simple. You go from point A to point B. Uh, but in reality, when these robots are deployed to the real world, they need to be incredibly redundant. You don't want robots stuck in the middle of a road somewhere. You need them to reach their destination and come home. And for that to be possible, they need to have very robust localization systems, such as what the robot localization package will give you once you learn to configure it. You might have also learned this word that I've been saying called Kalman filters, right? Um, Kalman filters in itself is a very critical part of robotics, but to be honest, if you ask me about Kalman filters, I could talk to you till tomorrow. But for the purposes of this presentation, we'll be thinking of them as a very simple filter. A filter, think of it like a system with a bunch of valves. We give it a set of inputs, right? We give it a set of measurements, and then it will perform a calculation, which in this case is a prediction. It will compare with our values, and then over time, it will produce a value of our pose based on our input values that is far more inaccurate than the individual values themselves. What do I mean by this, right? And let's see this in practice. Let's see this in a simulation. So for that, let's launch our simulation. By the way, there will be a lot of writing, and this is for the folks who are getting the ROS check, so the hands-on members. There's a lot of writing and theory that goes on, and if you're interested, please feel free to do the reading, it's quite interesting. And I have linked some interesting articles that I've gone through with the process of making this ROS check. So let's go ahead and launch the BotBox simulation and see what we're working with. So we can copy this command, and wherever it says execute in terminal, just open the terminal web shell. So you can see I have one open, and here we go. Then you can just paste the command and click enter, and it will execute the command. The simulation, which is the gazebo simulation, it will launch in this tab. If it doesn't launch automatically, you can click it. So I'm going to resize it here. Yeah, and you can see our gazebo is loaded. This over here is our tortoise bot, which we'll be working with throughout this session. This tortoise bot has a wheel odometry and an IMU on board. But this simulation is a little bit special from the regular simulations. It's because it simulates something that most don't. Now that we have it running, let's see what the topics are, right? Let's do a little bit of investigative work. ROS topic list, and we can see, excellent. This is a camera, interesting. We have the gazebo topics, and then we have an IMU, and we have an odometry. Perfect. We can double check if this is actually odometry by checking the topics information, and we can see, yep, it is of type odometry. So it's an odometry message. So now we have the odometry topic, right? We need to figure out, so we know because we're doing this this lesson that there is something wrong with the odometry. We can't just rely on odometry because it's not perfect. But we need to figure out why it's not perfect. What is the issue in this odometry? What is the error in our system? And to do this, there are many different ways of calculating this error. The most simple way, right, is if you have a real robot, even in the simulation, you can just put the robot down. You can tell the robot to move a certain distance. You can compare the distances, that is the calculated distance that it moved versus the actual distance that it moved. And from that, using a very simple formula, you can calculate your positional error. You can calculate this for X, Y, and then combine them together to form a one cohesive error. And then once you have this, if you're going to move around a lot, you can do this a lot of times. You can plot it out, and you will have basically a chart, something like this. The actual distance that you get is actually what's called a ground truth. And this is something that you will see in a lot of research, in a lot of academia. This is what ground truth is referring to. It's the real life value, so to speak, of the value. And this is going to be a reference point for comparing whatever models that we have for pose estimation. Now, the big expensive labs, they have these cool motion capture setups that give them, centimeter level position accuracy. But for us, we actually have something better in this case, which is, since we're running in a gazebo, we can just pull from the gazebo. So you can see in the gazebo, inside that model state message that we saw earlier, that there is actually pose and orientation information that we can use. For this, we will create a new package called Autumn Detective. So this detective is going to subscribe to these two values, and it's going to chart out, for one, our actual autumn and the actual ground truth. So this is going to let us compare the two values, and it also will calculate an error automatically, so we don't have to do the manual work. So let's copy this, paste it into our terminal. At this point, you can open the code editor, resize, and there we go. Until that loads, we'll go through this. First, let's create a detective.py script. You can resize it like this. Go into detective. Inside this, let's create a new file called detective.py. Let's paste in our script. Now, we won't go too much into this script because it's just a small tool to demonstrate the issue, but the code is there for the hands-on members, so they can feel free to check from there. Paste, perfect. Then we can just go through the most important part in this case, which is our calculating the error. So this is the simple formula that it uses to calculate the error, which is it calculates the difference between our ground truth and our ORAM for X and Y, and then combines them together via a square root. So let's continue on with the setup of our script. Let's get the setup.py. This is what will help us, it'll help the package see where the executable that we created is, which is the Python file. It will also help the package see where the launch file is that we'll be creating. So let's create that launch folder. And inside that launch folder, let's create a new detective.launch.py. When you're creating these, make sure they're in the proper folder, otherwise the script can't see them. Okay. Now we'll copy this our launch file, and there we go. Here we just connect to our detective node, and we give a set of real life, and we have a parameter that says real life, which is what checks if it's in the gazebo or not. If it's set to true, then we won't check with the ground truth, and we'll see that later. And this is the autumn topics that we are going to subscribe to. So now let's build and let's launch this package. As you can see, no errors there. And soon enough, it should open graphical tools. If it doesn't automatically open, you can just click it and you should see our graph is plotting. Now you can see it immediately shooting up, but something you will also need to notice is look at the axis. It's very, very small, which means it's almost minuscule. That means the only thing you're seeing is really just the noise. And that's something you'll be seeing comes in important later. And this little dot is there for the ground truth and ORAM. It's just a dot because we haven't moved yet. So let's do that. Let's move. We're going to use the teleop command to move the robot. Let's move this over here, our terminal. Let's paste our command. You will see some instructions for how to move around. And let's open our gazebo window. Let's resize it so we can see where we're going. Let's do a little L shape, right? We don't want to move too much. If you have the hands on, feel free to play around with it. Okay, so we've done a very simple shape, and you can see our graphs being charted. So you can see as it starts out, the error is it's pretty much spot on. There's no issue. But the moment I did that turn, you can see the ground truth and the autumn started to deviate. And this deviation only really grew. And you can see that in the discrepancy. This spike is there because of this, I believe. But what you should be looking for is this round baseline, which is a zero, close to zero. And now it's at 0.1 1-ish. So you can see the autumn error actually spiked, and it's not really tracking well with our ground truth. So this is an issue, right? This is telling me that though there is some kind of problem that's preventing the autumn from being close to reality. Now, given that this is a differential drive robot, given that this is sort of like a turtle bot, and this is using wheel odometry, can anyone tell me what this source of error might be? Anyone in the chat? I'm looking at it right now. I think it's being updated. I don't think it's being updated. Ricardo, do you mind telling me from the chat if anyone can guess correctly?
Yeah, we're looking. This is wheel slippage,
Oh,
wheel
yeah,
slippage.
yeah,
Yeah.
yeah, cool. I think it's Ivan, right? Okay, perfect. Wheel slippage. Now, this will come in important later when we're doing the configuration for our EKF pose estimation. So let's make a package now that launches that, right? So let's close this down. Let's close that, and let's close this. To close stuff, you can just use Control-C, right? Simulation, we can keep running, actually. Now, let's copy-paste this into our terminal, and that will create the new package for us, which is the BotBox EKF package. We need to create some folders. One is our inside of our BotBox EKF. Let's create a new folder for config. And inside config, let's create a new folder called ekf.yaml. Okay, perfect. Make sure it's in the folder properly. Now let's create a launch file, just like before, and inside a launch directory. So ekf.launch.py. If you are following along, the instructions are right here, so you can refer to it if you get a bit stuck or if I'm moving a little bit too fast. Okay. Now that we created these new folders, we need to let ROS know where they are. So let's modify our CMake lists. And this is basically just adding the launch and config directory to our final build. Now this is where the magic starts. The magic happens in the config, but this is where the magic starts. This is where we include our robot localization package, and it's pointing to the EKF node executable. Now there's two modes. There's EKF and UKF, I believe. There are two different types of filters, but for today we'll be using external Kalman filters. And we just name it EKF filter node, and then we have this parameter which is pointing to the config. And the other one is just use SimTime because we're running in a gazebo. Okay, so now that we pointed to our EKF config, let's start building our EKF config, right? This is the important thing. This is the controls for our valves that's working with the filter. So we're talking to the filter directly. So we'll get the header out of the way. This is just specifying these are the parameters. Now, first thing, we need to give the frames, right? Map frame and autumn frame. This is going to be pretty much the same in a lot of cases, unless you have some special naming scheme. The base link frame is going to be base link by default, but sometimes in some robots, it's base footprint. So you might want to modify that based on your TF tree. The world frame here is using autumn for this example, but if you're using something like AMCL, which is for like NAV2, for global localization, or if you're using something like GPS, then you'll want to modify the world frame to something else instead of autumn. Now our sensors. So we know we want to use wheel odometry and we know we want to use IMU. But I'll talk about why IMU in a bit. So, now, great. So for sensor inputs, you can have any amount of sensors as you want. There is no limit, but there are 4 types of message types that it supports. which is ORM, pose, twist, and IMU. When you want to list multiple of them, you just list the ORM, the message type, and an ID. So here I have ORM 0. So if I have another source of ORM, let's say I have like laser scan matching, I just say scan match or whatever the topic is. And I can combine them that way. Once you have the topics, then you need to give a config for that topic. And this might look a bit weird, but it's actually pretty simple. This is just an array of booleans. Think of them as like a big switch box, right? You want to switch on or off what data you're giving to the filter. So in this case, we're giving the absolute positions of x and y and the yaw velocity, and everything else we're not giving to the filter. We're not letting the filter touch, which means the filter will get this message and then it will drop this information and then it will go to the filter. For a planar robot, we typically want our x and y, which is our x and y positions, and our x and y velocities, yaw and yaw velocity. We don't really need z, we don't need z, because, well, we're not a holonomic robot, so we can't go in z. I mean, we can't go in y, and we're not a helicopter, so we probably couldn't go in z. So we're going to ignore that. In case of these, if you can give as much of these as possible, that's really good, because in terms of the sensors that are useful, in terms of the values that are useful, giving all of them is the best case in this. But giving all of these values is not. And we'll get to why. Now, why are we adding the IMU? You know, IMU seems so random. You know, it just seems, why are we adding the IMU? Especially if you know something about IMUs, is that if you use them to get positional information, they are trash. You don't want to use an IMU for getting positional information because they just get more inaccurate with time. So why would you use an IMU? They are not really accurate at positional information. They get more inaccurate over time. So why would you use it? It's because the IMU is good at a few sets of things, and that's giving acceleration values and giving orientation values. Now, we won't really be using orientation aside from the yaw, but acceleration is useful to us, which is our x. So x and yaw, we will combine together with our odometry so that in cases like we measured before, where our odometry and our ground truth is starting to shift, we have another sensor that's telling it, like a wingman, that's telling it, hey, I know you said this, you're going this far, but I'm taking a measurement of acceleration of this much here in this point in time. So maybe it's better to go in this direction. And that will give you far closer to the ground truth than just using ORM. And we'll see this in action soon. So let's copy this initial configuration, right? And we'll go through what it is. So we know that we need x position, y position, x velocity, y velocity. So we're giving that. And then we're giving the x velocity, and we're giving the yaw velocity. And that's pretty much it for our RODOM. And for our IMU, we're going to give out our yaw velocity, and our acceleration. Now the IMU looks fine, and we won't touch the IMU for now. But for the ODOM, I want you to notice something, and it's that I give the absolute x position, y position, and I also give the x velocity, and I didn't give the y velocity. Now we'll put the y velocity aside for now, right? But I give the x and y. But really, I shouldn't. And here's why. How are we getting this x and y? Right? So if we think about the core issue, right? And it's wheel slippage. Wheel slippage, the way that the wheel odometry works is that they have an encoder inside of the motor, right? The encoder can calculate the velocity based on how many turns the wheel does in a given amount of time. So the encoder is very good at giving the velocity. So encoder knows at all times how many times the wheel spins, or how fast the wheel spins, really. But it doesn't know if the wheel ever touched the ground, right? You could be holding the robot up and the wheel could be spinning, but the robot will just think it's going forward. So this x and y is actually calculated based off of this x velocity and y velocity. So trusting it as an absolute position is actually very bad in this case, and we don't want to give it that. The reason why you would give an x and y position is if you had something like GPS, where that absolutely gives you an x and y. Or if you had some other method like ICP odometry, which calculated it in a different way to give you x and y position, then you would fuse that together. But in this case, we don't want to do that. Another thing now is the y velocity. We didn't give the y velocity. Why? It kind of makes sense, right? It's not a holonomic robot. It can't go y. So why would we give y? But the reason we're giving y is precisely because it can't move y. When I set this to true, the odometry message will give 0.0 as the y velocity. And that's important. That's an important distinction. When this gives 0.0, that tells the filter that it's absolutely not moving towards y at all. Now, we don't want to enable that for our IMU. Why? Because our IMU is always going to give some value of our y velocity. Why? Because it has some level of noise inside of it. So the only reason why we would be seeing an acceleration for y is because of noise. In most cases during normal operation, unless you maybe like slammed your robot to the side, like you wanted to harass the robot, you would never get a y velocity or y acceleration. So it's best to set this to false in this case. So now we have our setup, right? We have our setup, our basic setup. There's one other thing, important side note, and then a very important thing. An important thing is the covariance matrix. There are two sets of covariance matrix. One is your process noise covariance and your initial estimate covariance. Think of this like as the gains in a PID control, right? These are things that you can tune to make the system better. These are typically not things that you tune when the system is not working. This setup in and of itself should make sure that the system is working. Once the setup is working for you and you want to increase its performance, then you start tuning these values. Not all of these values. You see this diagonal here, and that corresponds with your XYZ, etc. You can change the values here and here as well.
Thisas, 7 minutes to go.
Right. So the next thing is we'll set it to 2D mode. We'll put it up here. This will make sure that the robot, the system ditches anything that's unnecessary for 2D. It will ditch everything that's unnecessary for 2D operation, which is like our pitch and our pitch and our roll, just because our robot's never going to go those directions. So let me rebuild the package. Right? Okay, perfect. And now our EKF is running, and now we will run our detective, and let's run our. Okay, perfect. Now you can see the odom filtered, and ground truth. Now let's run our keyboard, and let's look at our simulation. We'll do the same exact movement. Probably not as precisely, but that's okay for now. Okay, close enough. Okay. So something you'll notice is that immediately the odom filtered sticks a lot closer to ground truth than odom is, which means it's a lot closer to the reality than odom is. And you can see that also with the odom discrepancy, which means our error in the system is much lower with our odom filtered than a regular odom. Now that we know our filter is working in the simulation, let's try it in real life. Because why would you want to test it in a simulation when you can test it in real life? And that's because this simulation is special because we have an exact replica of this simulation running in a real robot, in a real setup at the construct in Barcelona, and we'll be connecting it to it now. So our BotBox robot, and we'll be connecting it to it. Okay, so this is not sponsored, but this robot kit that you can buy for education, it comes with these 3 of these robots that you can use. Okay, let's resize that. It comes with 3 of these robots and the full environment. So if you wanted to teach something, maybe test out an open class on a real robot in your own labs, then I would suggest it. And just like that, let's test our system, right? Enough talking. We'll do a small modification because the topic is different on the real robot. Okay. And now let's build and run the package. Okay, perfect. It's running. Now, if we ROS topic list, we can see with topic list, we can see our new filter topic. Perfect. Okay. Now we can run our detective in real life mode, which means since there is no gazebo, we'll be just comparing the 2 topics together. Okay. And just so we can see a little more information, we'll be launching RViz with another config that will show the 2 sources of odometry. Okay. Now that we have it running, let's move our robot around and let's see how our system reacts. Demo gods, please answer my prayers. Let's see it. Let's do the same shape on the real robot. We'll do a small turn here. And then we'll run. Okay. Now let's see our gazebo. And what you will see is right now it's almost exactly the same. So if I turn one off and turn another one on, it's in the same exact position. This is mostly because in real life, the odometry is actually not as bad as in the simulation, but we can still move around more and see more features that our filter gives us. Okay. Okay. So you can see catching up. The red is our filter, and the green is just the auto. You can actually see small dots. It's not very visible here, but you can actually check the covariance of the 2. And this is something that is done by the Kalman filter, which is combines the covariances together, so you can visualize that. Okay, I think that sums up pretty much the basics of Kalman filters. Ricardo, if you have any questions, I think we can move on to that.
Excellent, Thisas. So thank you very much for your presentation. A big applause to you. Excellent. The people here in the chat were saying that this is awesome and very dense. So we need more time with you in order to understand all the knowledge that you have put in there. But now it's time to questions for Thisas. And as you know, there is a Q&A tab here on the top, on the side of the chat, where you can put your questions or also to vote for the ones that somebody else has done. And I will ask the most voted ones to Thisas. By the way, how is pronounced your name?
Thisas is okay.
Thisas. So, okay.
Yeah.
We thought that you pronounce it in a different way. Okay, no problem.
No, it's okay.
Okay, great. So, no problem. Then, let's go. Let me ask you a question in the meantime that they are putting the questions there and voting. My own question is, which other sources of state estimation can be mixed using the robot localization package? Because here you have mixed the odometry with the IMU, but what else can we add into those Kalman filters?
Yeah, so as I was saying during the setup, there's no limit on how many sensors, what types of sensors you can put in. It's just the limit is there on the 4 types of message definitions that you can put in, like odom, pose, IMU, and yeah. So there's like 4 message definitions that you can put in, but as long as your sensor can comply with the Rep 105 standards, then your sensor will work. So visual, odometry, if you're doing laser scan matching, if you're doing GPS, that will all combine together just fine.
Excellent, excellent. So then here there is one question from Josh Shewe that says, how to use robot localization with navigation too? So how can you combine this?
Good question. So remember when I was talking about the map frame, right? And I was saying that it's ODOM for now, but if you're using AMCL, you can change that. So yeah, that's where you would modify that. You can combine it to work with AMCL so that it fits in with the rest of your localization stack. If you are looking for how to configure this exactly and doing the full stack, I suggest maybe doing one of the courses on robot localization at the construct, because there is a very good course that you can follow. If you want, I think Alberto can link it on in the chat.
Okay. Yes, thank you. But let me suggest a couple of ways. So about that, so one could be, for example, just the odometry that you are getting, you can feed into the AMCL, because now the odometry that you have filtered with, which combines wheel odometry and IMU, is like a better odometry. Then you can provide this better odometry to AMCL, so AMCL can use it for their computations of the proper localization. Then this localization will be better because the odometry is better data also. Another way is to combine AMCL with the odometry and the IMU on the same filter. And so you will have the combination of those two. So those are also two possible ways of combining. And then I have a question from Angel Lopez that says, are you aware about Fuse package?
I wasn't until I looked it up. Fuse seems like a stack for sensor fusion.
No idea. It says, I have been told that the people who develop robot localization are encouraging to use Fuse instead of this, but the documentation was short a couple of months when I searched about it. So you haven't heard about Fuse?
No, a lot of the current like documentation and a lot of the current like tutorials and everything is mainly focused around robot localization, and that's just because robot localization was something that was big in ROS 1. So when that was to ROS 2, you can actually use pretty much close to the same configuration YAML for ROS 1 and ROS 2. Just a few things you have to change, I think. So that's mainly why robot localization is, I think, if you want to learn, it's no problem. You can learn with robot localization. The important thing is understand the concept of how the fusion works, and then you can apply that same concept to whatever package,
Yeah.
So understand the basics and then move forward with there. I suggest, actually, if you want to work with localization, try to understand about Kalman filters, like how they work. Which is another course that's there in the construct. So if you want to learn more about Kalman filters, you can maybe visit that course. But
okay. Then, but we'll keep an eye on that Fuse package, because I also don't know, and then maybe it's interesting to jump into that. Then another thing that says, another question is, John Seway is asking, so how did you plot the data in real time?
Oh, Matplotlib, Python, just combine it together.
Yeah, but how are you doing this? So you have a subscriber to the topics and then using...
Oh, for plotting,
Yes.
my implementation for plotting, let me revisit that actually.
Yeah, actually, it's in the project. So if you have access to the
So I
project,
have
then
I have an update plot function that gets called from I have a timer. So the timer calls the update plot function, and that makes sure that that runs on a separate thread, and that's how we continuously update it. So the X and Y gets into a local not a local variable, but into the self.oram data, self.ground truth. I continuously update that array, and based off of that array, update plot pulls from that array to do the processing. It's not really global. It's not a global variable, but it's global to the local to the whole class. So you can see the init function. Actually, I can screen share this.
okay.
Probably.
Yes. So I think that showing it will be better than explaining or more clearer.
Yeah. Okay. So you can see the ground data, ground truth,
Wait,
and errors.
yeah. Wait a second, because we cannot see yet. Sorry, it's in our location. Can we show the now we can see your screen.
Okay, perfect. Okay, so you can see here that I define 3 dicks. One is for the forum data, one is for the ground truth, one is for the errors. And then what I have is I have a callback called update plot that gets run on a timer. In this timer, I have this small script which basically sets the label. It adds the data. So for each thing in ORM topic, it plots it, and this continuously runs on a loop. So you can see where it gets flashed on the canvas. This took a little bit of debugging. It's a bit of a pain, but it kind of works. I think for the people who have access to the ROS check, they can feel free to copy the code. Or maybe I will reuse this in an open class so people can just take it from there.
Okay. And the next question from Ivan War that says, any note on visual odometry libraries for ROS2? So are you aware of any of them?
For visual odometry in ROS2,
yes,
is a little bit sparse. You can look for ports of a lot of popular visual odometry libraries that were ported from ROS2, but honestly, I wouldn't. Some of them are working, some of them are not. Especially if you're sort of resource constrained, I wouldn't go towards many. But the one library that I would suggest in many cases would be to go towards either OrbSlam.
OrbSlam,
OrbSlam 3. Yeah, OrbSlam 3 works in a lot of cases. Or there's this thing called OpenVSlam, which is pretty good. OpenVSlam, but it's less a bit stable. It was forked, and the fork is updated, but not the original repo. So there are some situations. There is a really good survey on GitHub, which goes through each of them because there are a lot. I put that in the chat.
Okay, excellent.
Okay, so you can see from there a lot of ROS1 options, some ROS2 options. If you just wanted to implement it for a project, just go with OrbSlam. It's easiest.
Okay, great. One question from Sebastian Castro. How do all these tools do time synchronization? So it's all based on the ROS message timestamps, or do you have use any other tricks?
Can you repeat that?
Yeah. So how did you time synchronize the different odometries? So you can show them on this on the position at the proper, so they are matching one to another. And so if you are using just a message timestamp, you know that all of them, they have a timestamp, and or you are using your own trick. What's happening? Have we lost Thisas?
To combine that, it's based on the timestamps.
Oh.
So it,
Hello, Thisas, are you there?
oh,
Yes, we can
you
hear
hear me?
you. Yes, we can hear
Yeah.
you. Go ahead. Yes, we can see you. So what
Okay.
about the timestamps?
It's based on the timestamp. It's based on the timestamp. So the filter will take the data in based off of the timestamps, and you can make the filter itself go at a specific refresh rate or specific like number of hertz. I think it defaults to like 30 or something, and it will use the timestamps to synchronize them. I'm not sure if it does exact synchronization or not.
Mhm.
You would have to refer to the documentation for that one, I'm afraid.
Okay. Then thank you very much, Thisas. We don't have more time for questions. Thanks a lot again to our speaker. Thank you. See you around. Thisas.
Thank you, Thisas.
Okay, see you. Bye-bye.
Very nice presentation, especially the real robot part. Really love that. So, yes, dear attendees, now you should see the box on your chat in order to rate this speaker. So take a moment to do so, because remember, when we finish this conference, we will announce the best speaker based on your votes.
Absolutely. So, before we see the next speaker, so I believe maybe all of you can guess what we're going to do now.
Oh boy.
Dear. No,
I think I know. I think everyone knows.
Yes, it's prize quiz time.
Oh, yeah.
Yes. The winner will get another super sweat box with the Robotics Developer T-shirt, mugs, and the stickers. So this is sponsored by the BotBox by the Construct. And we will watch a 5-minute video about the BotBox. So at the end of the video, again, you will see a question related to this. And the first person answers correctly will win this swag box. So you may need to go to the page of the sponsor to get the answer. So now let's watch the video, and the next speaker will hit back in 5 minutes.
See you soon, guys.
See you soon.
See you soon.